Imagine a senior AI agent tasked with redesigning a complex microchip. Right now, in most frameworks, that agent is probably trying to explain its hardware logic in English, getting totally confused by its own massive context window, and, well, ultimately failing.
Yeah, and that's exactly why we need a paradigm shift.
Right. But what if we stopped forcing AI systems to speak our fuzzy, ambiguous language, and instead forced them to live entirely inside their native physics? I mean, executable code. Welcome to AI Paper Podcasts. If you are an ML engineer, an AI researcher, or really anyone building autonomous systems, we are jumping straight into a massive new framework today that fundamentally changes how you should architect your agents.
That's a huge one, yeah.
The paper is titled Code as Agent Harness Toward Executable, Verifiable, and Stateful Agent Systems. It's authored by a team of researchers from UIUC, Meta, and Stanford. And for the short-form summary, their core thesis is that large language models have traditionally treated code merely as a target output to be generated. You know, you prompt, it spits out Python, and you're done.
Right, just a one-off transaction.
Exactly. But in modern, complex agentic systems, code is no longer just the output. It has become the operational substrate. It is the underlying infrastructure, the harness, as they call it, for how an agent reasons, takes action, models its environment, and verifies its own execution. This paper provides a unified roadmap for building these systems, breaking them down into 3 layers: the interface, the internal mechanisms, and scaling to multi-agent environments.
And, you know, the urgency for this shift really comes from the fact that we are hitting a hard wall with natural language. As agents move away from being simple chatbots and start taking on long-horizon tasks like complex GUI automation, enterprise-level DevOps, or open-ended scientific discovery, relying on natural language for reasoning and coordination just completely breaks down.
It's just too ambiguous, right?
Exactly. English is lossy, and the agent's understanding of the task drifts over time. By treating code as the literal infrastructure of the agent, we ground its behavior in objective, executable truth. A program either compiles or it doesn't. A test suite either passes or it fails.
Yeah, there's no gray area.
Right. Using a code harness forces the agent to anchor its abstract intent to a rigorous, testable reality before it makes its next move.
So let's look at the first layer of this roadmap, which is the harness interface. This is the actual connection point between the agent and its environment. And the paper separates this interface into 3 distinct roles. Code acts as the reasoning substrate, the action interface, and the environment model.
Yeah, and starting with the reasoning substrate requires rethinking how we prompt models. Like, the industry standard has been chain of thought prompting, where an agent explains its logic in a paragraph of English before outputting an answer. But that relies entirely on natural language reasoning.
Which we just established is too lossy.
Exactly. When code becomes the reasoning substrate, agents externalize their internal logic into verifiable, executable steps. Think of giving the agent a live Python scratchpad. Instead of generating a sentence that says, I will now calculate the sum of these rows, the agent actually writes the pandas data frame operations, executes them, and uses the objective numerical output as the foundation for its next logical leap.
Okay, let's unpack this because the implications are massive. It's like the difference between a philosopher and a mathematician.
Well, that's a great way to look at it.
Yeah, like a philosopher can sit in an armchair and think abstractly about a problem in natural language. Their reasoning might sound incredibly elegant, but it is subject to interpretation, hidden biases, and logical leaps that are very difficult to catch until the whole argument collapses.
Right. It's hard to test a philosophy.
Exactly. But a mathematician, however, writes out a formal proof on a chalkboard. Every single line on that board can be objectively tested and verified by the strict laws of math before moving to the next line. Using code as a reasoning substrate forces the agent to take its internal monologue and write it out on a verifiable chalkboard.
That analogy captures the mechanism perfectly. And, you know, once you have that chalkboard, it naturally evolves into the second role, the action interface. Code becomes the literal mechanism that translates an agent's abstract intent into executable actions in the real world.
And we aren't just talking about an agent acting as a junior developer writing a web app here.
Yeah. No, not at all. We're talking about code that interacts with external tool APIs, code that renders UI actions to click a button in a web browser, or even code that sends torque commands to physical embodied robots in a laboratory. The action isn't a text description of what the agent wants to do. The action is the compilation and execution of the function itself.
Which means the environment the agent operates in also needs to be translated into this language. That's the third part of the interface, right?
Yeah.
Environment modeling.
Right. The structural translation of the world is where many current systems fail. Because how does an agent actually know the state of the world around it? Traditionally, a system might use a vision model to look at a screen and feed the agent a text summary saying, there's a login button on the top right.
Right, relying on natural language again.
Exactly. But in a true code harness, the environment is modeled entirely programmatically. If an agent is navigating a website, the environment isn't a paragraph describing the visual layout. The environment is the document object model, the DOM state represented as a queryable tree of code. The environment becomes action APIs and visual grounding mapped directly to pixel coordinates in a mathematical array.
So by capturing the world as code, the agent can track complex dynamics and execute automated checks to verify if the state has changed as expected after taking an action.
You got it.
So the agent has a perfect, queryable snapshot of the environment in code. But if a task takes 3 days to complete, say debugging a massive enterprise code base, how does it keep track of its progress without its context window overflowing? I mean, an interface is completely useless without internal mechanisms to sustain those long horizon tasks.
Yeah, sustaining those tasks brings us to the second layer of the framework harness mechanisms. For an agent to survive a complex, multi-day objective, it relies on planning, memory, and tool use. And what really stands out in this research is how the concept of working memory has functionally changed.
How so?
Well, in early large language models, working memory was just a growing wall of text in a context window. You appended every action to the prompt until the model forgot its original instructions. But in advanced stateful systems, working memory is a live code environment. It operates like a Kodak-style RPL, a readable print loop.
Ah, okay.
Yeah, the agent's memory actually consists of live variables sitting in RAM, active data frames, and persistent function states, rather than just text tokens in a prompt.
Maintaining that live state over thousands of steps requires intense feedback, though. The paper introduces a concept for this that I found incredibly compelling called deep telemetry.
Yes, deep telemetry. It fundamentally replaces the standard error log. Consider a shallow log in a traditional software pipeline. It provides a binary signal at the very end of a process like task completed or test failed.
Right, which isn't very helpful for an AI trying to learn from it.
Exactly. Deep telemetry records the microscopic details of every single interaction. It logs the exact prompts used for every subtask, the specific retrieval contexts fetched from a vector database, the token usage per minute, the network latency of every tool call, complete sandbox snapshots of the environment before and after an action.
Wow.
Rejected alternative code branches the agent considered but discarded, and the full stack traces of any errors. It builds a complete structural optimization substrate.
Okay, wait, I need to push back on the mechanics of that, because if you are listening to this and you maintain an enterprise MLOps pipeline, you know how massive logs can get.
Oh yeah, huge.
If we are recording every single token, latency metric, stack trace, and rejected sandbox snapshot, aren't we just going to drown the agent in data? I mean, how does an AI system actually process this deep telemetry without completely blowing past its context limits and forgetting its overarching goal?
That concern highlights a very common architectural mistake developers make when building these systems. The deep telemetry is never shoved verbatim into the agent's working prompt.
Oh, okay, yeah.
Doing that would instantly crash the context window. Instead, deep telemetry serves as an inspectable substrate that lives in the external environment, usually an equal database or a structured file system. The agent uses feedback-driven control to query it iteratively.
Okay, so it pulls just what it needs.
Exactly. If a test fails on day 2 of a task, the agent doesn't need to read the entire 2-day history. It writes a quick SQL query to pull the specific stack trace and the sandbox snapshot from the exact millisecond of failure. It uses the telemetry for targeted, iterative debugging, completely avoiding prompt stuffing.
I see. It's like building an indexed archive. It can search dynamically. Rather than stuffing everything into a backpack, it has to carry around for the entire journey.
That's a perfect way to put it. And the paper highlights 2 brilliant systems leveraging this kind of deep execution feedback in the real world. The first is a system called MGE, which automates hardware and microchip design.
Okay, microchip design.
Yeah, and in hardware development, getting a simple pass or fail on a test bench is virtually useless for debugging. So BEMS EG provides the finest grained execution feedback possible by implementing a waveform window. It records the electrical signal values at every single clock edge.
Wow.
Yeah, when a failure occurs, the system doesn't just say the design is broken, it delivers a literal waveform snapshot isolating the exact failing clock cycle back to the agent for analysis.
So it isolates the issue down to the physical properties of the code. It literally tells the agent to look at the voltage on a specific pin at nanosecond 42.
Exactly. And the second system, MacRo, tackles a different problem performance profiling. Instead of just checking if a piece of code produces the correct output, its telemetry measures execution time, memory usage, and floating point operations per second, or FLOPS.
Right, the efficiency of the code.
Exactly. But what makes MacRo unique is how it responds to those metrics. When it identifies a bottleneck in the FLOPS, it autonomously runs web searches to retrieve specific algorithmic optimization techniques from recent computer science literature.
Wait, really?
Yeah, and then it rewrites its own code to implement those specific mathematically proven optimizations.
It measures its own runtime and efficiency, reads research papers on how to fix it, and patches itself. It's wild.
It is.
And zooming out from macro naturally transitions us to the next massive challenge. We've established how a single agent operates inside this executable harness, managing its own memory and querying its own telemetry. But modern enterprise-scale tasks require multi-agent systems. And the moment you add more autonomous agents to a project, the coordination complexity scales exponentially.
Oh, absolutely. Scaling introduces specialized workflow topologies. You no longer deploy one generic AI to solve a problem. You deploy a manager agent, a planner, a reviewer, a tester, and a coder. And they operate in distinct modes. Sometimes they're collaborative, handing off subtasks in a pipeline. Other times they're adversarial.
Like red teaming.
Exactly, like in debate setups or red teaming scenarios where one agent generates code and another agent aggressively tries to find security exploits to break it.
But the researchers isolate a massive bottleneck in how the industry currently builds these multi-agent teams. They call it the central gap.
Yes, the central gap is arguably the most critical vulnerability identified in this survey. Currently, the vast majority of multi-agent frameworks rely on what the authors call implicit or file-only state.
Meaning what exactly?
Meaning they lack a formal, queryable, shared model of the code harness. Instead of interacting through a rigorous shared database that tracks the absolute state of the environment, the agents essentially talk to each other in natural language to try and figure out what is going on.
All right, so they're back to natural language.
Yeah. The coder agent sends a text message to the reviewer agent saying, I just updated the API to handle concurrent requests, and the reviewer agent just has to trust that natural language summary.
So what does this all mean for the final product? The central gap sounds like a team of human architects trying to build a massive skyscraper by only texting each other descriptions of what they just drew on their personal sketchpads.
Right.
Instead of all collaborating on a single interactive 3D CAD blueprint. Like if I text you, I move the load-bearing wall slightly to the left, your LLM might imagine something completely different than what I actually coded. All that context management, the endless messaging back and forth to keep the agents synced, is just a massive computational tax we pay for not having a formal shared state.
The communication tax is massive, and it introduces compounding hallucination risks. But if the entire team operates directly on the executable harness, ambiguity disappears. The load-bearing wall is mathematically proven to be a coordinate X, or it isn't. This shared executable state allows multi-agent systems to achieve what the paper calls harness state convergence.
Which answers the hardest question in AI automation.
Yeah.
How does a team of autonomous agents definitively agree that a complex task is actually done?
Precisely. Because the shared environment is executable code, agents stop relying on conversational agreement. They don't just output "looks good to me" in a chat log based on a text summary. They rely on objective execution signals to reach consensus.
Like what?
Well, the paper details several convergence frameworks. Candor, for instance, uses majority voting among 3 independent panelist agents who don't evaluate the code itself, but evaluate the compiled execution outputs.
Oh, interesting.
Yeah. A framework called Meiji Eyes relies on a dedicated LLM QA engineer agent whose sole function is to execute massive test suites. It provides a hard gating signal. And Quality Flow uses a deterministic code quality checker as an early exit gate.
Got it.
The system only converges and stops iterating when the code passes rigorous, objective execution checks. The execution is the ultimate source of truth, not the consensus of language models.
Pushing this shared blueprint concept to its absolute limit brings us to the final and frankly most mind-bending section of this deep dive. To truly understand the power of closing the central gap and utilizing code as a fully shared infrastructure, the researchers point to the most demanding high-stakes application imaginable: end-to-end scientific discovery.
Yeah, the authors posit a radical reframing here. We should view scientific discovery as a partially observable program world. They take the messy, deeply human process of the scientific method and map it directly onto a standard reinforcement learning loop.
Right.
They express it as a mathematical tuple, SATO.
Okay, let's break down how those reinforcement learning concepts map to actual laboratory science, because this is where the theory hits reality.
Right. We start with S, the state. In this framework, the state of scientific progress isn't a vague concept. It is the active program memory. It represents the current best hypotheses stored as variables, the downloaded literature embedded in a vector database, and the active code artifacts representing experiments.
So that's S. Then if S is the current state of our knowledge, the agent needs to take actions to advance it. But these actions aren't a scientist physically mixing chemicals or adjusting a microscope. In a code harness, the actions are typed code expressions.
Exactly.
An action is an API call to a molecular solver, an automated SQL query to a global protein database, or a Python script that sends coordinates to a robotic arm in a wet lab.
Which triggers T, the transitions. Taking an action changes the world. In traditional reinforcement learning, the transition function dictates how the environment updates. In this program world, the transition function is literally the compiler or the interpreter.
Right, it runs the code.
Yeah, it is the Python engine executing the data analysis on a new chemical compound, or a formal logic kernel algorithmically proving a theorem. The interpreter physically transitions the state of the experiment.
Generating the observations, or O. The output of that compiler transition becomes the data the agent sees. It reads the numerical results from the physics simulator, parses the error messages from the compiler, or even ingests peer review scores generated by a separate reviewer agent evaluating the novelty of the findings.
Leading to R, the reward, the ultimate optimization target. In science, the reward function mathematically encodes desiderata like statistical significance, physical reproducibility, and mathematical novelty.
Here's where it gets really interesting. When you frame the entire scientific method as a reinforcement learning loop governed by a code harness, the boundaries between human concepts like ideation, experimentation, and writing completely collapse.
They do.
They stop being separate phases of work. They all just become a single homogeneous flow of typed code objects moving through an interpreter.
Yeah, the pipeline becomes entirely unified. The paper highlights several real-world implementations, proving this isn't just theory. Take AI Scientist, versions 1 and 2. It represents an entire machine learning research paper as a single executable trace.
A whole paper.
A whole paper. The system writes the experimental PyTorch code, executes the training run, uses a vision language model to literally analyze the matplotlib graphs it just generated, and then natively outputs the final manuscript in LaTeX, a code-based typesetting system used by academics.
Wow.
The initial hypothesis, the training loop, the visual analysis, and the final published paper are one continuous execution loop.
It's writing the code, running the code, looking at the graph, and writing the academic paper about the graph.
Right.
All autonomously.
Yeah. Another implementation is ChemCrow. It doesn't just read about chemistry. It grounds its LLM in the code harness to compose 18 different expert-designed chemistry tools. By leveraging executable code, it can predict chemical properties, search reaction databases, and actually send execution commands to cloud-connected synthesis hardware.
That's incredible.
Then there is AlphaProof, which tackles pure mathematics. It forces the agent to express its complex reasoning steps as lean tactics commands written in lean, a formal programming language used by mathematicians to algorithmically verify theorems. A proof assistant must strictly verify every single tactic before the agent is allowed to move forward, ensuring zero hallucinations.
And the long-term memory aspect of this unified pipeline is staggering, because the paper details systems like Agent Grox and Biomni, which rethink how scientific knowledge is stored across generations of agents.
Right. Biomni mines tens of thousands of biomedical papers from platforms like bioRx4. For a human researcher, learning how to clone a specific plasmid requires reading dense methodology sections and practicing physical techniques in a lab for weeks.
Yeah, it's incredibly slow.
But for an agent running Biomni, remembering how to clone a plasmid simply means importing a mathematically verified code protocol from its database. It turns complex lab know-how into a simple Python import.
That's wild.
And Agent Tariffs expands on this by allowing multi-agent systems to literally upload their final experimental findings to a shared preprint server as durable program artifacts. Future agents can download that exact state, import the prior agent's hypotheses, data frames, and functions, and pick up the research exactly where the last agent left off. It creates cumulative, fully automated scientific progress.
It's building an executable civilization of AI researchers. So, to bring this all together for you, the listener, whether you are building a tool to automate enterprise DevOps, architecting a multi-agent system for GI navigation, or trying to automate a chemistry lab, the mandate from this research is crystal clear. You have to stop treating code merely as the output text of an LLM. Code is the harness. It must be treated as the executable, verifiable state of your entire AI architecture. If your agents are just chatting with each other in natural language to manage their state, you are losing fidelity and bleeding compute. Ground their intelligence in execution.
Grounding intelligence and execution is the fundamental takeaway. But connecting this technical roadmap to the bigger picture raises a profound question we have to grapple with as an industry. We are talking about turning entire disciplines from enterprise software development to global scientific discovery into fully automated executable program worlds. By doing so, we are giving agents the ability to autonomously search, experiment, and optimize within those worlds at speeds we cannot possibly match.
Right.
So what happens when the optimization target, that algorithmic reward function driving the executable loop, subtly misaligns with human safety? If the entire physical world is slowly becoming a programmable harness for AI who is writing the ultimate test bench?